Okay, so we're going to revisit the problem with which you started week 1. And there you were asked to look at a piece of code that computed the polynomial given the coefficients. And those coefficients were stored in a one-dimensional array as P0, P1, P2, etc. up to n minus 1. And here we limit our polynomial to n minus 1 because that gives us n entries in our array. Now, in this particular section, you actually get the program. And the programming language that you are going to use is MATLAB. And MATLAB starts indexing at 1. What does it mean? There is no P0. There is an entry P1, and then P2, and P3, etc. through Pn. So let's start with that. Now, what we want to start with is the specification of the problem. And this is kind of a hand-wavy specification. So let's sharpen that a little bit and let's give the post condition. And the post condition R is then given in our notation as y is equal to the sum over the entries I such that 1 is less than or equal to I is less than or equal to n of P of I times x raised to the I minus first power. And that's our post condition. Okay, what have we learned? We have learned that we can come up with loop invariance by partitioning the quantifier in the post condition. And let's have a look at that. So to come up with possible loop invariance, what we are going to do is we're going to take y and write it as this quantifier. Plus the rest of it. And then we have to indicate what range k can have. So let's guess at that. We'll start by guessing that 1 is less than or equal to k is less than or equal to n. Let's think about that. If we take k to be 1 and plug that in here, then this first quantifier is over the empty range, so that becomes 0. And the second one is from 1 to n inclusive, and that's exactly our post condition. So that's looking good. If we then take k to be n, and we plug it in here, then this first quantifier is not quite what we want, because it's short the last term. And the second one actually still has one term in it. So we need to fix that, and the way you fix that is by saying that k can actually go up to n plus 1, because then the first part is exactly the post condition, and the second part is summation over the empty range, which is 0, and everything is good. So now what we have is an expression from which we can try to derive some loop invariance. And how might we go about this? Well, one possible loop invariant is to say we're done with the first quantifier, and we haven't done anything for the second quantifier yet. And if you think about it, what algorithm do you get? You get an algorithm that computes the result one term at a time. And that's a matter of going through the motions. What about another one? Well, you've seen before that often we can say take away the second quantifier or take away the first quantifier. So we could take a loop invariant where only this has been computed and this has not been computed. I call it striking it out. I'd like to just put a big scratch through it or erase it altogether, but we'll leave it there and let's picture what would happen if we take that away. And if you think about it, what that particular loop invariant would do is it would give you an algorithm that would start computing the result one term at a time backwards. All right? Now, the annoying thing here is that every time you compute a term then, you would have to take x, raise it to some power, and multiply it by the coefficient and add it to a partial result that you've computed so far. And raising x to a power is expensive. We'd like to not do that. Wouldn't it be nice if very systematically we can come up with algorithms that avoid that? And it turns out the answer is yes. And how do we do that? Well, if we look at this right here, this really captures pk times x to the k minus first power plus pk plus 1 times x to the kth power, etc. And one thing that you notice is that there's a common term, there's a common factor x to the k minus 1 in all of these. So we can take this away and this away, etc. and write this as times x to the k minus first power. Okay? And what does that mean? That's the same as saying factor out x to the k minus 1, but we can't just factor out like that. In order to do that, we have to subtract off x to the k minus first power, and that's a matter of adjusting the exponent here. And then, if your algebra is somewhat decent, you recognize that this is just x to the I minus kth power. And this now gives us all kinds of options. We can have a loop invariant where we still strike all of this out. We saw that one before. We can take the loop invariant where we strike all of this out, and that actually gives us the one that goes backward through the summation. But we can now also say, gee, if we don't want to recompute x to the k every time, we can take this and we can store it in a variable. Let's call it z. And if we then specify that as part of our loop invariant, then every time through the loop, z will be updated by multiplying it times x, thereby computing the powers x to the k as we need them, which you can then use to update the variable in which you're accumulating y. Okay. But there's one more there. And the final one is, don't do this, do this, and take that away. Okay, so what is that loop invariant? That loop invariant takes away this part right here, and it takes away this part right here, which means we don't need a temporary variable z. Now that's a really odd one, because what you notice is that at no point in the algorithm is the final result computed. Okay? Every time you compute here, or every time you go through the loop, what this here says is that there is a partial computation that has been done, but it's not that some part of the total summation is finished, where you have finished with all of the terms. And that may seem really odd at first. But what I want you to do is I want you to trust the force. Okay? Trust what you've learned. You come up with a specification for the postcondition. You come up with candidate loop invariants. If you can derive an algorithm from the loop invariant, then you have proven that algorithm correct, and therefore you know it will give the correct answer. And just do it and see what comes out. And then once you're done actually implementing it, and hopefully you will derive it to be correct, so the first time you ever run it, it will give the right answer. When you're then done, we will discuss what this actually means. So go to it.